Welcome, ladies and gentlemen. Let's take a look at our Bellwork today. If p of x is increasing, what must be true about p prime? Marissa? It must be positive over the same interval of concern. So positive first derivative indicates increasing behavior for my original function, and that's old news. Sketch a portion of a graph that's both decreasing and concave down. So decreasing and concave down. I saw that many of you kind of had that. So we need decreasing, right? The function values are getting less and less as you move along the curve from left to right, and doing so, right, at a quicker rate. And so here we've got this concave down shape, which resembles part of an upside down bowl. Is it possible to sketch a graph that is decreasing and concave up at the same time? Decreasing and concave up, right? What would that look like, Riley? Like that, man. Right? That would be decreasing and concave up, and so we could certainly do that as well. I don't really like that picture. I don't know. Much better. Actually, no? All right. So let's go ahead and take a look at our third then. A function fails to be differentiable for any of these reasons, and I neglected to include one in our summary IVT day last time, and so I want to make sure we hit it this time. So what's one? There's lots of reasons. So what's one reason that a function could fail to be differentiable? What's one reason? Tyler?
It's a discontinuity.
Yeah, if there's any kind of discontinuity. So if there's a discontinuity, then my function fails to be differentiable. We have three different types of discontinuities. So within the discontinuity realm, right, I want to go ahead and get those specific types. So what's one type of discontinuity, Vivian? Absolutely, an infinite discontinuity. That would be like a vertical asymptote. What other kinds of discontinuities do we have? Courtney? A step discontinuity, where the left-hand limit as x approaches c does not match the right-hand limit of f of x as x approaches c. So a step discontinuity. And what's our final kind when the overall limit does exist, and yet it's still discontinuous? Sophia? Yeah, the removable discontinuity, when we have a hole, the overall limit of f of x as x approaches c exists. That is, the left-hand limit matches the right-hand limit, but for some reason the function is not defined to equal that overall limit. So there's that hole in the middle where we could fix it. We could plug that hole by redefining f to take on the value of the overall limit at x equals c. Awesome. So discontinuity is my first problem, right? If there's any sort of discontinuity, then f fails to be differentiable at x equals c. But there's other ways that f could fail to be differentiable. So what's another way that f could fail to be differentiable at x equals c? Grace? Yeah, if you had a corner where the left-hand slope value exists and equals some finite value, and the right-hand slope value exists and equals some finite value, but those values are different. And so the left-hand slope exists, the right-hand slope exists and equals some finite value, but they're not the same. Therefore, the overall slope does not exist. And if derivatives refer to the values of the slope of a function, then the overall slope doesn't exist, means that the derivative does not exist. Classic example would be our absolute value function, right? Where the left-hand slope does not match the right-hand slope, and yet they both exist and equal a finite value. And then my another reason then would be, Kobe? A cusp. This text goes a step further and splits up corner and cusps and says that the slopes become infinite, either positive infinity or negative infinity on either side of x equals c. And so a cusp is when we have that slopes becoming infinite on either side and opposite values. And then one we neglected to include that I want to make sure we included this time was similar to a cusp, right? Except that it's not different values of infinity on either side as x approaches c. So in this particular drawing, as x approaches c from the left, my slope values are approaching negative infinity. And as x approaches c from the right, my slope values are positive infinity. If they were approaching the same infinity, right, the slope still does not exist because an infinite slope is no slope, right? An infinite slope is undefined. The slope of a vertical line is undefined. But we still have not differentiable because that slope does not exist. And so that would be a vertical tangent. So vertical tangent, I want to make sure we include that. Where again, we could be smooth, right? We could be a smooth function, we could be continuous, and yet not differentiable because we've got a vertical tangent. A classic example would be like the cube root function, right? Y equals the cube root of x, where I've got smooth function, but we've got a vertical tangent here in the middle, so the slope is undefined. Bless you. Awesome. Questions about today's Bellwork? Let's get going then. We've got a double check, and so I want to do two separate checks, please. First, I'd like to check our review, and I'll pause the recording while we do this. Okay, ladies and gentlemen, today we're going to do a short activity. It's not very long, okay? It'll only take a little while. You're still going to work together in your cooperative learning groups, and after the last group's gotten their 10C stamp, we're going to come back together, and we're going to have a whole group discussion for a little bit, and then you'll have a chance to get started on your OTL, okay? And so today we're going to explore extreme values. We're going to take a look at some piecewise defined stuff, because that's kind of where we left off with a lot of our differentiability questions with those piecewise defined functions, the left-hand function definition versus right-hand function definition, or left-hand slope values versus right-hand slope values. And so this is a great place in BC to take it to the next level. We're going to go ahead and get stamped at 5E, 8B, and 10C. When the last group's gotten your 10C, we're going to come back together and have whole group, and then we'll have closure after that. Awesome. So without further ado, let's go ahead and pause the recording and get into our groups. Okay, ladies and gentlemen. So let's come together after exploring extreme values. We want to go ahead and get a common vocabulary for several of our terms.
Just don't know about.
Oh no. All right. So if f is continuous on a closed interval, a to b, then f has both a maximum value and a minimum value on the interval. Well, this makes perfect sense, regardless of which function we were looking at in the exploring extrema activity. We had a continuous function, yes? So guaranteed, if we have a continuous function, then there must be some maximum value attained, which is greater than all other function values on the closed interval, and there must be some minimum value attained, right, which is less than or equal to all other function values on the interval. Even a constant function has a maximum value and a minimum value, because the definition for a maximum value is that it's greater than or equal to all other function values on the closed interval. And so this makes perfect sense. What we need to add, though, is a definition for critical points versus stationary points. This text makes a distinction with one of the cases for a critical point and calls it a stationary point. So let's go ahead and add our critical point definition. Y is said to have a critical point where y prime equals 0 or y prime is undefined. And this was your 8B stamp. Your 8B stamp explored the two different cases where an extreme value occurs on your original function f of x. If f prime of x equals 0 or f prime of x is undefined, these are the only places where f might change direction, which could contribute then to a local extreme. So that's why we have critical points. That's why we make a big fuss about critical points, while they're called critical, because it's the only place that y could change direction, and that would contribute to a local extreme. Now, I'm going to go ahead and squiggle underline could. Right? The only place that the y could change direction. Doesn't mean that there's automatically a local extreme value at x equals c if f prime of c equals 0 or is undefined. No, we certainly could have a plateau point, which we saw last year in AB, where the slope is 0, right? It levels off like in the y equals x cubing function, right? Y equals x cubed levels off, but then continues increasing after the fact. That is not a local maximum at x equals 0 for the x cubed function. All right. An additional new vocabulary term for us is stationary point. Y is said to have a stationary point at x equals c when y prime equals 0. So one of these two places, if y has a horizontal tangent, then that's said to be a stationary point on y. Y prime need not change sign at a stationary point, right? Y prime just has to equal 0. So y equals x cubed has a stationary point at x equals 0, but so does y equals x squared. My total bowl shape function, that still has a stationary point at x equals 0, just because y prime equals 0. In the second case, y prime changes sign. In the first, it doesn't. Doesn't matter. To be a stationary point, we just need y prime to equal 0. In other words, y has a horizontal tangent at a stationary point. That's for you. Okay. So what, right, does the mean value theorem do for us? Well, we've been investigating extreme values where we've had f prime being equal to 0 or undefined. These are places where y could change direction. If we add this next component, our mean value theorem from last year, we'll now have a powerful tool and a means for finding optimal solutions. That is optimization, and that's the main focus still for the BC curriculum in addition to the AB applications. First though, let's recall that if f is continuous on a closed interval a to b and differentiable on the open interval a to b, then there exists an x equals c value in between a and b such that f prime of c equals f of b minus f of a all over b minus a. What the heck does that mean? Well, we saw f prime of c is my instantaneous rate of change, as opposed to f of b minus f of a all over b minus a. That's my old school slope calculation from algebra 1. That's my average rate of change. Graphically, my instantaneous rate of change of a function f at x equals c would be the slope of the tangent line to the curve at x equals c. And so my instantaneous rate of change could be interpreted as the slope value of the tangent line to the curve at x equals c, as opposed to the average rate of change. Graphically, that would refer to the slope of the secant line connecting the endpoints of my interval a to b. All right, I want to make a graphical representation of this. So, slope of the secant line connecting the endpoints. So let's go ahead and make a graphical connection for our mean value theorem. Let's go ahead and draw an arbitrary function on an interval a to b. We can label our x values for our interval a and b respectively. On our y-axis, we could go ahead and label our y values as our function values, f at a and f at b. If my function f is continuous on the closed interval a to b, notice I've got my closed circles there, and differentiable, do I have any corners? Any kinks? Any discontinuities? No? Vertical tangents? Nope. And so if we're continuous and differentiable on that interval, then there must exist some x equals c value in between a and b, such that what? Well, such that the slope of the tangent to the curve is exactly equal to the slope of the secant line connecting the endpoints. So let's go ahead and put in our secant line there. First, I'm going to use my line tool for this pretty sweet. Pink, pretty in pink. So there's my secant line. And I want to see where, right, on that interval a to b, the slope of the tangent is equal, is parallel, is the same. So it looks like right about there comes in and touches tangent to the curve. And so it looks like if I came down now, there's my x equals c value. Is it between a and b? Yes, it is. And so that's old school mean value theorem for derivatives last year. Very important because it allows us now to find, right, to find maximums and minimums in the special case where my slope of the tangent is horizontal. Right? My slope of the tangent is 0. All right, let's go ahead and do a couple practice now. We want to decide if the mean value theorem applies. Keep in mind our prerequisites for the mean value theorem. We must be both continuous and differentiable on the interval a to b. If it does apply, then let's go ahead and find a particular x equals c value that satisfies the mean value theorem. So I just gave you a blank template. Yes? All right. So surprise, first one is f of x equals secant x on the interval 0 to pi. First we need to decide, does the mean value theorem apply? Well, in order to do this, we need our function to be continuous and differentiable. And when I think about my definition for secant, I'm having concerns right away because I know as a fraction, secant can be rewritten as 1 over cosine of x in accordance with our reciprocal identity for secant. Is there any place on the interval 0 to pi where I have issues with the domain of secant? Are there any places where on 0 to pi would I have issues? Courtney?
Pi over 2.
Yeah, at x equals pi over 2, right, cosine of x equals 0, and so I know that this function is undefined at x equals pi over 2. Therefore, since pi over 2 is on the interval 0 to pi, I know with that discontinuity that the mean value theorem, right, is not guaranteed to apply. Now, incidentally, the mean value theorem, or we might be able to find some x equals c value where the slope of the tangent is parallel to the slope of the secant line, but we're not guaranteed that one exists unless f is both continuous and differentiable on the integral. So no, the mean value theorem does not apply. So that just made for a very quick problem. Well, I hope we have more fun on the next one. Let's take a look at another. F of x equals 5 over x plus 1 on the interval 0 to 4. Let's think about what that looks like back. And so on my function definition, f of x is given by 5 over quantity x plus 1. I know the only domain issue I'd have in this function definition would be from the fraction if the denominator, x plus 1, were ever to equal 0. Will that equal 0? Well, certainly. X plus 1 will equal 0, but it'll do so at x equals -1 only. Is x equals -1 on my interval of concern? No. Does this spoil the mean value theorem? No. The mean value theorem does apply on this particular interval because f is continuous and differentiable. My only concern was if the denominator in that function definition ever takes on the value of 0, and it does so, but it's not in my domain. So what do? We say yes. The mean value theorem can be applied. All right, so what does the mean value theorem say? Well, it says that if my function is continuous and differentiable, check, then there must be some x equals c value on my interval such that the slope of the tangent, f prime of c, is equal to the slope of the secant line. That is f of b minus f of a all over b minus a. Can we find those missing pieces for this function? Yeah, we have the function definition. So let's go ahead and get my f of b. In this case, f of 4. Let's get my f of a. In this case, f of 0. And we can go and do our slope calculation. Then we'll take our derivative, f prime, and set it equal to that slope of the secant line to see where x equals c satisfies the mean value theorem. All right, so here we go into the original. At x equals 0, what is that? 5 over. Are you guys getting 5? Yes? F at 4. 4 plus 1, 5. 5 over 5 is 1. Yes? So my slope of the secant line equals f at b. Let's do it. So f at b minus f at a all over b minus a. How's that? Is that good? Yes? So my slope of the secant line is 1 minus 5 is -4 over 4 is -1. I guess you need -1. Now we need to determine if my function, right? My function derivative f prime takes on this value. Well, no need to determine that I know it takes on that value. The mean value theorem guarantees that somewhere along the instantaneous rate of change of that function is equal to the slope of the secant line is equal to -1. We just have to figure out where. So let's get my function f prime's derivative. I'm sorry, my function f's derivative. Call it f prime. We'll do that using our derivative rules. This looks like -5 over x plus 1 quantity squared, as we've done more and more of these. You could rewrite that as a negative exponent and do the power rule. Yes, is that right? Or use your knowledge of the derivative of the reciprocal function that we've done. All right, so let's go ahead and see when my function f prime equals -1. So let's go ahead and set them equal to each other. Let's see when this happens. So how do I want to solve this? I'll multiply that x plus 1 quantity squared. Divide by the negatives, right? Does that ever happen? Well, I'll go ahead and take the positive and negative square root to get my x plus 1 quantity alone. And I'll finish it out by subtracting my 1 over, and I get -1 plus or minus √5. What? Let's go ahead and see, right, at x equals -1 plus √5, let's compare that derivative value with the slope of the secant line, -1. So here we go. We've got lots of ways we can check this. First, let's go ahead and get a viewing window that's nice. So 5 over x plus 1. We want 0 to 4. 0 to 4. So I'm going to go ahead and purposely set my window manually. Let's go ahead and do -1 to 5. And let's do -1 to 7. All right, I don't know if this is, did I get more or no? I don't know how good this is. But I'm dying to see. That's not a mean value theorem joke. Yes? Okay, so how can we check? We could check by doing second, calculate. Which option would I use? I could use that sixth option, and I want to calculate the derivative at the algebraic x value we determined for C, which was 1 plus √5. So -1 plus √5, good catch. If we're correct, when I press enter, right, what should happen? The lights should dim, the ground should shake, right? Minimal tremor? No. The cursor should jump on the curve, right? And it should spit out the dy dx value, what? We're hoping. Gosh, didn't work. Oh my gosh, it did work! The x value and the y value, right, are from the point of the curve, and it looks like my dy dx value is -1. Great. What's my other x value? Right, what's going on there? Well, I algebraically solved, and it generated two c values because I undid the square root. However, is the other x equals c value on my interval of concern -1 minus √5? No, that's going to be over on the other branch, and so we don't need to include that as the x equals c value. It's not on my interval. Good. Algebraically, we generate it. And so what do? Well, we can strike that because it's not on my interval. So x equals c. My special x equals c value is -1 plus √5. There's just a single value on the interval. That's pretty sweet. Awesome. Does the mean value theorem apply? F of x equals cube root of x on -1 to 8. Awesome. So does the mean value theorem apply on -1 to 8 for f of x equals cube root of x? Go ahead and tell your partner, Kylie. All right. So is my function continuous? Right? Is my function continuous, Danny?
Yes.
Yes. Is it differentiable? No, it's not differentiable. And so while I've got continuous smooth function right here, right, we've got that vertical tangent, and so therefore the mean value does not apply. Okay, the mean value theorem does not apply, and so no, I guess I want these on this page. Vertical tangent right there. Therefore, the mean value theorem does not apply. All right. What else do we need? We need a little practice with our first derivative y prime in determining extremes as a result of our exploring extreme activity. So let's go ahead and take a look first at our polynomial function. F is given by x to the fourth minus 10x squared plus 9. And let's use analytic methods to determine the intervals of increasing/decreasing behavior and local extrema. Then we'll verify graphically. So I've got my emulator on hold. I'm totally in trouble. I was worried about my cube root function being well behaved, and now I'm worried about you guys being well behaved. So what are we going to do? Let's go ahead and get f prime involved. So here we go. First derivative, f prime is given by, and what do you have for that, Brendan?
3x. No, 4x3, sorry.
Good.
Minus 20x.
Good. Now what do we need from f prime? Well, if we're determining intervals of increasing and decreasing, I saw you on your guys' 5 things that you guys listed. Some of them are fairly creative with your symmetry. I must point out that when y prime is positive, y is increasing. When y prime is negative, then y is decreasing. So what are we going to do? We're going to find those critical values by seeing when f prime is equal to 0 or undefined, just like your AB stamp. Will f prime of x, 4x cubed minus 20x ever be undefined? No. So since f prime is defined for all real x because it's a polynomial, I only need to consider when it equals 0, and that'll be my sole source of critical values. And those are my potential extremes, local extremes. So what do we do? Set equal to 0, let's solve. Factor first or fail, right? So I'm going to go ahead and pull out my greatest common factor. Looks like 4x. Leaves me with x squared minus 5. 5. Very nice. Well, does this ever happen? Yeah, it looks like it happens when 4x equals 0, or x equals 0, and when x squared minus 5 equals 0. And does that ever happen? Yeah, at x equals plus or minus root 5. Yes? So we've got how many critical values? Yikes, we've got 3 critical values. So we've got critical values at x equals 0 and plus or minus root 5. Let's go ahead and make a f prime number line. So we'll label it f prime of x, and we'll put on our critical values negative root 5, 0, and root 5, and perform a sign test to determine the sign of f prime on each of these subintervals. That will now tell me about the increasing versus decreasing behavior. So let's examine the sign of f prime to determine the increasing versus decreasing. So no problem here. Let's choose a convenient x value on each subinterval. Recall that negative root 5 would be in between negative root 4 is negative 2, and negative root 9 is negative 3. And so I'm thinking if I choose negative 3, I'll be in this leftmost subinterval. So negative 3 into my f prime. Wouldn't it be nice if I had my f prime over here? Yeah? Oh, math works. Sorry. Love it. Figure 3. Negative. Positive. Yes. Overall. Negative. Negative 1. Negative. Negative. Overall. Positive. Positive 1. Positive. Negative. Negative. And 3. Say 3. Positive. 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 What, if anything, have we learned? Well, it looks like F's decreasing wherever F prime is negative, so F decreasing. On negative infinity to negative root 5, union 0 to positive root 5, because that's the prettiest little cursive I've seen in a long time. F prime is negative on those intervals, and F is increasing. On negative root 5 to 0, union root 5 to infinity, because F prime is positive on those intervals. Uh-oh. All right, last thing, local extrema. When F prime switches from negative to positive, F switches from decreasing to increasing. So what feature does F have at x equals negative root 5? Kobe?
Minimum.
A minimum, right? A local minimum, because F prime switched from negative to positive. So we've got, or this. So F has local minimum, and we know the x coordinate, negative root 5, but a minimum value is a function value, a y value, and so we have to determine the y value if we're asked for the minimum value. What do we do there? We'll plug in negative root 5 to my original. I'm going to label this. All right. So into my original, negative root 5 goes. Negative root 5 to the 4th power is positive. Root 5 times root 5 is 5. Root 5 times root 5 is 5 again, so I'm getting 25 minus 50 is negative 25, plus 9 is negative 16. You guys can check me out. So I have a local min at negative root 5, negative 16. We'll get the same thing when we do positive root 5, because it's to the 4th power and to the 2nd power. So I'm going to go ahead and put 2 here. And lastly, F has the local maximum value at 0, comma, and I have to evaluate. I got this one, guys. Nope, let me. 9. Oh, good stuff. Okay, polynomials, so easy, right? It's so 2000 late, I'm getting 80 flashbacks. What about x ln x, right? More of a transcendental function. Let's take a look at that. So g of x is given by x ln x. Now we'll go ahead and use analytic methods to analyze the behavior of g. What do we need? We need our, oh, darn it. We didn't verify graphically. Oh my gosh. I'm going to say, given our recent success with the emulator, that would totally pan out, because I'm more interested in this composite transcendental function x ln x. And so I'm going to hold off on the graphical check if that's okay with you guys. Let's do g prime. So go ahead and calculate g prime ratio of the class. Go. And I'll call on you. Okay, what are you getting for your G prime? What are you getting for your G prime? Tyler?
ln x plus 1.
Ln x plus 1. Raise your hand if you have the same as Tyler. Ln x plus 1, good. The derivative of the first 1 times the second is ln of x plus the first x times the derivative of the second is 1 over x, and that reduces to 1. Nice job. Why do I care about G prime? Because the sign of G prime anywhere along it will tell me the increasing versus decreasing behavior of G. So what do? We get our critical value. Are there values of x that make this undefined? Certainly. G is undefined whenever, right, whenever my x input is non-positive. So that would happen at x equals 0. It would happen at x equals -1. It would happen at any non-positive input. However, that is in my original domain of g of x because ln of x is there. So I don't have any undefined values on the interior of the domain of my function g. Therefore, I don't have to include x equals 0 as a critical point because I'd be including x equals -0.000001 also, and also x equals -0.00000001, and also x equals negative. So all those non-positive. So we're going to preserve the domain of my original, and we're going to consider if this ever equals 0. When will that happen? Well, that will happen if ln of x equals -1. I thought we just said that we couldn't, right, have negative inputs in the natural log function. Well, we can't have negative inputs, but this is a negative output. Does the natural log function produce any negative outputs? Certainly, right? It's beneath the x-axis everywhere in between 0 and 1. And so we exponentiate to solve and get base to the exponent equals input. This happens when e to the -1 equals x, or x equals 1 over e. We'll go ahead and grab my g of x function, g prime of x function. Tyler told us ln x plus 1. Yes? And we'll make our g prime number line and label it g prime of x. We'll throw our critical x value on there was 1 over e. And choose a convenient value on either side of the interval. Recall this is capped, right? This function does not exist to the left of or equal to 0. So what do we want to choose for in between 0 and 1 over e? 1 over e squared? 1 over e squared? Yeah? So 1 over e squared is e to the -2. ln of e to the -2 is -2. Plus 1 is -1 is -2. Choose a convenient x value to the right of 1 over e, like e. ln of e is 1 plus 1 is 2 is positive. Yeah, we're expecting to see a local minimum at x equals 1 over e. Awesome. So first I'll say g. Gee whiz. G is decreasing on strictly 0 to 1 over e because g prime is negative. You see we're getting into Mr. Fritz's shorthand notation in the interest of time. And g is increasing on 1 over e to infinity for the same reason. G prime is positive on that side, and g has local minimum at x value 1 over e, y value go to the original. So I get 1 over e times natural log of 1 over e is e to the -1. E to the negative ln of e to the -1 is -1 times 1 over e is -1 over e. So we're guessing -1 over e. And we totally scrambled for that because we know we're going to check and we're going to be like, oh, math works. I love calculators. I take this on B-days too. And my window is going to be -1 to 3 and -2 to 3 and We'll try that. How can I check? Can I write a check? Yeah. Yo, trace 1 over e. You guys just see that? You guys just see that? Third time is charm. Yeah! Why am I yelling? Oh, because I recognize that that's 1 over e, then that must be negative 1 over e. Yes, I knew we were going to get this. And, bless you, it's not a moment too soon. We are so good because we're here. So y has a critical point. One is, don't say out loud, just write down, be ready to share. Oh, I hate when Mr. Britt says the fill in the blanks. In order for y to have a local minimum at x equals c, y must blank, blank, blank to blank? No idea. No idea. I'll come back to you guys. In order for y to have a point of inflection at x equals c, y must blank, blank, and y double prime must... Oh, so we're getting at what y does versus what y double prime does in order for y to have a point of inflection. Well, I'll be interested to see what you guys come up for that, because I have no idea. So y has a critical point when two scenarios, right? So what are our two possibilities for y having a critical point? Vivian?
It's 0 or if y prime is 0 or
Good. Y prime equals 0 or y prime is undefined. Raise your hand again, both of those possibilities. So y prime equals 0, y prime undefined, good. In order for y to have a local minimum at x equals c, y prime must, so what did you say for that, Courtney?
switch signs from negative to positive.
Good. So we've got to switch signs from negative specifically to positive. Awesome. Raise your hand again, the same thing. Y prime's got to switch signs from negative to positive. Good. And in order for y to have a point of inflection at x equals c, y must, Marissa?
Change from capital.
Good. Which means that y double prime must, Marissa?
Change sign.
Good. Up. Change sign. Way to go, you guys. That's awesome. And guess what? I now determine your OTL exercises. So there wasn't enough on the printable, but it's okay because I just had question mark, and now I have exercises. So OTL 1, you'll have to write down. Notice the prevalence of odd exercises here, except for your 9 to 11 is all. So I'll go ahead and stop the recording and save it. Great work today, you guys.